Thanks to the organizer for inviting me and giving this opportunity to talk in this conference. So, as the title suggests that I will talk about equivariant bundles and toric variety. So first we have to fix the notations. So I'll start with a very quick notation. So all my objects are over complex number. And so let T be the complex torus, N be the one parameter subgroup, you can identify with Zn, and M be the character group. So toric variety X of dimension N is an algebraic variety with a that admits an algebraic action of T with a dense orbit we call it O is isomorphic to T. So some facts, there are finitely many orbits. So these orbits are indexed by cones. So one can give an explicit definition of what is a cone, but cone is a convex linear combinations of co-characters. So I denote by sigma. So I will not go to the what is definition and all. So these are cone sigma in N. So that means that any sigma, you can write it as summation lambda I xi, where xi belongs to N, and lambda I are positive. So anyway, I will not go into detailed definition what is psi equal to 1 to k. So, and I need what is dimension of sigma. So dimension of sigma is the smallest dimension of the smallest subspace in Rn containing sigma. So, and if I, so for a sigma, so O sigma is the orbit, correct? So orbits are indexed by these cones. So O sigma is a isomer. If sigma is of dimension k, then O sigma is isomorphic to C star n minus k, where n is the dimension of x. So what are the examples? So projective space, weighted projective space, Book surface or any blow-ups of Pn at the some finitely many points. So with this description, of course, this X, you can write it as union of these orbits and so there are finitely many cones, so this is a finite disjoint union. But it has another description which will be useful. So this X sigma, where each X sigma is A sigma cross O sigma. And if so, and there is a gluing of these X, so X sigmas are so affine, so these are affine T varieties. So these are stable under this T action. So the gluing data, so there is a gluing going on, so this gluing data is given by the collection of cones. I mean, cones, how do the gluing data is given by the collection of cones. So which is, so there is some property that if you take two cones, then it should intersect, and so these are called fans. So anyway, I will not go to the definition of for what is a fan and all, but I don't need this for this talk. So, but one thing is important, that the open orbit, the O which is isomorphic to T, this is inside every X sigma. So for each X sigma in fan. The collection of cones, I call it sigma. So I denote it by. So if I take a point in the, say, in the orbit corresponding to sigma, then I denote, so suppose dimension of sigma is k, so call it X sigma. Then the stabilizer group of X sigma, I call it T sigma. So this T sigma is isomorphic to C star or K. Where? So this identification, you can identify T with T sigma cross O sigma. And of course, X sigma is identified as so because O sigma is T mod T sigma, so you identify, you can think like this. So one thing is notice that these A sigmas are also, A sigma is a toric variety under T sigma. And if A sigma, and if X is smooth, then each A sigma, then A sigma is C power K. So this is what we need for this talk about toric variety. this is a very, so this is the, I'm fixing the notations first. So now let's talk about vector bundles over equivariant vector bundles over toric variety. So a T equivariant, so a equivariant vector bundle E on X. So it has, so T will act on E and T will act on X. I assume I take T action on E is on left. So T action, so T acts on E by left action. So that it is the action, T action is fiber-wise linear, and this pi is T equivariant. So what does it mean? It means pi of T dot E is T dot pi of E for all T for all E. So when you talk about vector bundle, first you talk about line bundles. So denote sigma D the set of the d-dimensional cones. So if X is complete, then pick X is isomorphic to Z power m minus n. What is m? M is number of elements in sigma of 1. The cardinality of one-dimensional cones. So so that means so all line bundles has all line bundles has a T action, T structure or T action. But when you go to one more dimension, this statement is horribly wrong. I mean, so very few vector bundles has a T structure, non-trivial T action. So most algebraic vector bundles, most vector bundles, I'm talking about only algebraic vector bundles. So most vector bundles does not have T equivariant structure. So actually, so there is a, so you can prove that E over X is a toric variety, it's T equivariant if and only if T upper star of E is isomorphic to E for all T belongs to T. So this is a proof this is a proof given by Liachko first. So, so obviously, so this makes that equivariant vector bundle, T equivariant vector bundles are rigid. Because you can take a one parameter subgroup, so all T upper star E is isomorphic to E, so you don't have many. So these are rigid vector bundles. So they are the fixed point in the moduli space of vector bundles. So if you consider a moduli space of vector bundle, T will act by pullback action. So these are the fixed points of the moduli under the T action. Okay. So this is a so this is a result of Kliachko. That over X sigma, if I restrict my, suppose E is a vector bundle over X, equivariant vector bundle, T is equivariant vector bundle. Next. So then if you restrict your E to these X sigmas, these affine pieces, then this is T equivariantly isomorphic to V. So given by a representation where T action on V is given by a representation to this. T action on this is diagonal action under this rho sigma. So okay. So now, so now the question is that how do you classify, because there are not many T equivariant vector bundles, whether you can classify T equivariant vector bundles or no. So this is in this direction. So the question is classification of T equivariant vector. So this was, so first result was due to Kaniyama for smooth toric varieties. So first, for when X is smooth, this was first classified by Kaniyama. So this was done in 1978, published in Nagoya. So he has written two papers, I think 78, 79 probably, 79, 80, I'm not sure. So the first paper talks about the classification, and the second paper is more about the when a equivariant vector bundle splits, and he tries to solve Hartshorne conjecture for equivariant vector bundles. So see, he makes a statement that over Pn, and if E is T equivariant, then using his classification, he makes a state that E splits. If rank of E is less than n, then E splits, and E is T equivariant, then E splits into line bundles. So for rank equal to 2 and n equal to 7, greater than equal to 7, this is Hartshorne conjecture. For equivariant case, he tries. When rank of E is 2, and n equal to 7, n greater than equal to 7. So this is but Hartshorne conjecture, of course, is for any vector bundle, but this is the equivariant analog. Equivariant. But so after this, so I will not describe what is Kaniyama's classification, because I will try to do it for principal G bundle. So I will describe the Kaniyama's classification for principal G bundle, and if you take G equal to GLN, so that Kaniyama's classification follows. But another interesting classification. So here Kaniyama assumed that X is smooth, but if instead of smooth, if you take any, so this is a complex number even, and so one can ask in two directions. The generalization one is that what is the non-smooth case, or what is the non-zero characteristic case. So Klyachko classification answers both. This classification does not depend on the complex number. The base field is complex number, and it does not assume X is smooth. So this is Klyachko's classification. This was in 91, published in Izvestia. So what does it say? He says that this equivariant vector bundles, you can describe in terms of some linear algebra data. So, so how do you see this? So I'll give a very quick. So first I will write what is it, and then I will try to explain very quickly that how do you, from a vector bundle, how do you get such data. So, so what Klyachko says that T equivariant vector bundles, and this is a categorical equivalence. So if you take a category of T equivariant vector bundles, this is equivalent to filtration data. The category of filtration data. So what is a filtration data? So filtration data is it is E, comma F alpha I with certain compatibility condition. What is, so alpha belongs to the one-dimensional cone such that for each sigma, this E can be written as direct sum of E sigma U, where U belongs to the character of T sigma. Sorry. So this is such that F alpha I is equal to summation E sigma U, such that alpha U is greater than equal to I. See, there is between character, these are characters, see alphas are one-dimensional cone, so this you can identify with the co-characters. And there is a bilinear pairing between character and co-character. So that is the bilinear pairing. I mean. So this is called compatibility condition. And these F alpha i's are decreasing filtration. That means so they are, since it's finite, so it's a finite filtration. So and you can talk about the maps between two filtration data. It's a map from E to say E prime, which takes the filtration data to the filtration data. So this is the category of filtered, so sometimes is filtered vector space with a compatibility condition. See, I did not complete here. For all alpha belongs to sigma 1. See each, so this is a one-dimensional cone. Alpha is a one-dimensional cone, so this alpha will belong to some sigma. So for each sigma you have a decomposition. This is a T is, so for, because over X sigma, this is trivial, so T, there is a map from T to GLE, so that will decompose torus acting on a vector space, so it will decompose the eigenspace decomposition, and these are the character because T is abelian. So I'll quickly explain how do you get, starting from a vector bundle, how do you get such data. So by the affine case, you can, so if you start with E, so E, this is X sigma cross, say, E X sigma, phi bar at some point. Okay? So X sigma is some point in, you have to be a little more careful what is X sigma, but I am not, it should be in the unique closed orbit, but I am not going into such thing. So, and also this phi sigma, called phi sigma, the T action on E restricted to E sigma is given by some map, some linear map. So from T to out X sigma. So now, since E is a vector bundle, there is a transition function. So this is from X sigma intersection X tau, which is nothing but X sigma intersection tau. So in the fan description, you can intersect two cones. So these are transition function. So this is from Hom E X sigma to E X tau. Now, since it is a T equivariant vector bundle, this F sigma tau should satisfy this condition. Since E is T equivariant, T of X is equal to phi sigma of T, F sigma tau X, phi tau of T inverse. Because it's a T equivariant vector bundle. So now, this is for all X in X sigma intersection tau. Okay, so, so now you fix a point in x naught in the open orbit, which is isomorphic to T, which is inside in all x sigma. So in particular, it is in x sigma intersection term. Okay. So now, now see by the T equivariance, f sigma T x naught is phi sigma T f sigma tau x naught phi tau T inverse. Right. So now you have to make little bit adjustment. So you have to identify all these fibers, but I'll not going. So this you can do it. So for believe that this can be done. So this is my E and f sigma tau x naught to be identity on E. So in that case, so this is in the open orbit. Now what does the transition function says? So this T is sitting inside this. So on T, the transition function behaves so nicely. So if I assume this, so this is nothing but phi sigma T, phi tau T inverse. So now so it's a question of extension. When you can extend, given homomorphism phi sigma, collection homomorphism phi sigma from T to automorphism of E, when you can extend to the x the so this extendability condition. So first the T acts on this vector space. So this will say that for each by the action for each sigma there is action. So this phi so for each sigma I have this isotypical decomposition E. So I call it E sigma U, where U belongs to the so this is the isotypical decomposition. So define E alpha sigma of I to be direct sum of a sum of E sigma U, where U alpha is greater than equal to I. So for each for alpha belongs to sigma 1. Okay. So now now this alpha can be in another tau. So similarly you can define E alpha tau of I as, so suppose alpha, so I'll write like this. So suppose alpha belongs to sigma intersection tau 1. So it is in both sigma 1 and sigma tau 1. So similarly, E alpha tau I you define to be E tau of say V such that V alpha is greater than equal to I. Now the extendability condition will tell you that these two spaces are same. This F sigma intersection tau from T to or T extends to x sigma intersection x tau. This is equivalent of saying that E alpha tau I is same as E alpha sigma I. So that means this filtration I constructed is really independent in which cone alpha lies. So that means so for each one-dimensional ray alpha, I construct a filtration, and that is what my data is. And this is by construction. You see that the way I constructed this satisfies this isotypical decomposition because I have taken. So this is Kliatchko's idea to how to construct, and the opposite is true. That if you start with such a filtration, you can construct a T equivariant vector bundle on X. So this is very useful in classifying T equivariant vector bundles. Not only that, it has many applications, like using this filtration data, Kliatchko proved Horn's conjecture. And there are many applications, so I will not go into application. So you can, basically you can classify all equivariant vector bundles and, okay. So now, I will come back to principal bundle. So I assume G is a affine algebraic group. And X is a, so P is a principal bundle. With a left T action on P such that phi is T equivariant. So again, you can ask that when a principal bundle has a T structure, the answer is that if P is T equivariant, if and only if T upper star of P is isomorphic to P for all T. So this is a theorem. This we have proved in one paper. So this is Kliatchko's analog of T equivariant principal bundle for the for equivariant principal. So again, it says that the principal T equivariant principal bundle, so they are also rigid objects. So, so now the question is that how do you classify equivariant principal bundle? So this is, will stop at 3:30. This is 20 minutes gone or 20 minutes left? Oh, okay. Okay. So we want to classify equivariant principal bundles. So we will use a strong fact that X is smooth. Because X is smooth, if when X is smooth, so we assume X is smooth. So that means that this X sigma is A sigma cross T sigma. So this is C power K, and this is C star power N minus K, where K is your dimension of sigma. So we'll use this so in general, it's not known that over affine variety, the T equivariant principal bundles are trivial. So we will use this fact from equivariant Oka principle. So which says that if you have a principal G bundle on Cn or Ck, and if K is a reductive group acting, so it is P is K equivariant, where K is reductive, principal G bundle, then there exists a semi-equivariant section. So what does it mean? This means that there is a section from Cn to P such that T times Sx is equal to S of Tx times rho of T. So it says that this principal bundle P is equivariantly trivial first. Call it fiber at 0, and so action on P is given by the homomorphism from rho T to G, and there exists a semi-equivariant section which there is a section which satisfies this. So this section is nothing unique. So there is no canonical choice of a section. So rho from K to G, sorry, because the group acting is K. So now come back to X sigma. So you know X sigma is your Ck cross C star power n minus K. So by this, so you extend, see this K is your T sigma, because T sigma is T sigma is Ck is a T sigma toric variety. So you extend your homomorphism. So call this. So from Oka principle. So by the way, this is a theorem of Heinzner and Kutshebusch. So by Oka principle, you have a section X. So by Oka principle, there exists a section. So you extend. So from Ck to Ck power Ck cross C star n minus K, you extend your section. There exists a section S sigma from X sigma to G. To E restricted to X. So P restricted, so I am starting with P, so I'll write. What's that? And rho sigma, which is a map from T to G, which factor through T sigma. because the homomorphism you are constructing on T, whole T, by taking T mod T sigma, the action to be trivial. On T sigma, the action is action you are considering. And so T dot S sigma x is S sigma of Tx times rho sigma of T. So this is small check that if S sigma is semi-equivariant, then S sigma dot G is also semi-equivalent. So this is in the holomorphic setting. Okay, this is P is you start with the holomorphic principal G bundle. But in the algebraic case, if you take algebraic bundle, see this S sigma. If I take, for example, x equal to x naught, then S sigma of T x naught is T times S sigma of x naught, right, multiplication by rho sigma of T inverse. But if you take algebraic, so these are all algebraic action. So that means this S sigma of T x naught is algebraic. So that means that, and by limit of, so every point is limit of Tx naught. So by continuity, you can say that all S sigma Tx, these are algebraic. So it is true for, so for algebraic, because if you take an algebraic principal bundle, all these actions are, so S sigma of Tx is, this side is all algebraic action. So these are involving algebraic functions. So, and by limiting the continuity argument, you can say that for every x, so this is true for algebraic principal bundle. So this section is algebraic. Okay. So fix a point x naught in the open orbit, which is isomorphic to 2, which is in x sigma for all sigma. So define, so now you have for every sigma you have this section, x sigma. So you define P tau sigma to be S tau of x naught. This is uniquely defined because it's a principal bundle. So for each, because these are two, so it's a free action. So this is, and this P tau sigma satisfies co-cycles condition. So that means P tau sigma inverse is P sigma tau and P co-cycle condition. So now you define, so definition. So for each sigma, there is a homomorphism rho sigma which factors to T sigma and this P tau sigma. So it's called admissible collection if first is that rho factors through T sigma, second is this P tau sigma are co-cycle, are one co-cycle G-valued points. G-valued. And for every pair, so you need to extend from T to the x sigma intersection x tau. So for every pair, tau in sigma cross sigma rho tau p tau sigma rho sigma inverse extends to, so this is the like Cleach co-extendability condition to the whole X sigma intersection. And among this, you define a equivalence relation, the obvious equivalence relation. If you have two such admissible collection, if rho sigma and p tau sigma is equivalent to rho sigma prime p tau sigma prime, if there exists g sigma, for each sigma you have g sigma such that rho sigma prime is their conjugate. Sorry. And pt tau g tau inverse p tau sigma g sigma. So now the classification theorem is that isomorphism classes of equivariant principal G bundle and equivalence classes of admissible collection, there is a one-to-one correspondence. The theorem is isomorphism class equivariant principal G bundles. So we have to put isomorphism. This is not very strong condition like Cleach categorical equivalence because there is isomorphism involved. So we don't get a categorical equivalence. So because this choice of section is not a canonical, whereas Cleach because of isotypical decomposition is trying to say more. So this is one-to-one correspondence with equivalence class. Admissible connection. So in other words, when you have a T equivariant principal bundle, if you have such data, so you can construct a T structure on a principal. Basically, it is gluing of X sigma cross G with this identity, with this information. So converse is also true, like Cleach. So this is again by okay. So now in last 7 minutes, I will try to explain what is Kaniyama's classification. So I will explain for the principal bundle. So vector bundle also. Okay. So this theorem has some application, like you can really say what is the center of the group is sitting inside the automorphism of the principal bundle. In the usual case, the center sits inside the automorphism of principal. Here, center. So, so there are, and also if you, for example, if you take a nilpotent group, if G structure group is nilpotent, then it has a torus reduction because there is no map from torus to unipotent part. Any unipotent, you can write it as product of torus and the unipotent. So you have a reduction to maximal torus. So anyway, so since time is not there, I not talk about application. So I will go to straight to Kaniyama's classification. So recall that for every sigma I have this section S sigma which is semi-equivariant. So I fix some, fix an embedding. Suppose G is inside GLR, find algebraic group. So it is fix an embedding. And let K naught be the maximal torus, the usual diagonal one in GLRC. So I call a section S sigma. So I have this S sigma, S sigma from X sigma to P restricted to X sigma, and rho sigma action on G. So I say S sigma is a Kaniyama section. If image of rho sigma lies in this fixed maximal torus, which I call it K naught. So see all maximal torus, and see one thing you notice that if S sigma is a semi-equivariant section, then G dot S sigma is also a semi-equivariant. And the corresponding, so if you call it S sigma tilde, so if you call it rho sigma corresponding representation, then rho sigma tilde will be G rho sigma G inverse. So now you use the fact that all the maximal torus are conjugate. So for every sigma, so this torus will go to some maximal torus, so call it T sigma, but you can bring it back to this K naught because all maximal torus are conjugate. So for every sigma, I have a G sigma, or call it, okay, if you call it, you want to call it G sigma, such that which takes the maximal torus to this, and take the corresponding Kaniyama section, corresponding semi-equivariant section. So, so without loss of generality, we can assume that all this lies in the fixed K naught. So once you are in fixed K naught, then you know this rho sigma of T will be given by some characters. So call this xi sigma. So for each sigma, I have this R tuples of character. Now, this will satisfy such a certain condition. So, so this we have to check that xi sigma satisfy that eta of xi sigma I is equal to eta of xi tau of gamma I for some gamma of in SR symmetry group for all eta. So these etas are the characters. So for all eta in sigma intersection tau, so one intersection. So, so for every tau and sigma pair, define p tau sigma, which is an element in G, such that p tau sigma ij is not equal to 0 if eta of xi tau I is greater than equal to eta of xi sigma of G for all eta belongs to sigma intersection tau 1. So now I call it Kaniyama data. Is this collection xi sigma, which is a collection of character, and p tau sigma. So you can work with the maximal. So instead of working with all cones, you can talk about, you can do it only for the maximal dimensional cone, which is denoted by. So here, so this is the data, and here also, like before, you would call these two are equivalent. So if you call this xi p, if there exist gamma such that xi, oh, I have again went to this xi sigma 1 up to some permutation. So this is one condition, and the relation between p prime, similar condition for some gamma. Huh? Okay, so I'll just write down the final theorem. So, and p prime tau sigma is g tau inverse p tau sigma g sigma g sigma. There exists g sigma belongs to G such that. So the theorem is that again the isomorphism classes of T equivariant principal bundle has one-to-one correspondence with isomorphism. So Kaniyama data up to equivalence. So in case of GL and C, so Karniyama's description for the vector bundle was when you replace G equal to GL and C in terms of these data. You classify principal vector bundles over. So I'll stop here. I'll not talk about much about the application, but there are a few applications of this theorem. Yeah. So it will be, you are saying C star n cross CR, or if R is the rank of, I mean, GLR, I mean, I don't know, I mean, I don't know any equivariant bundle construction using GIT, so I don't know. But probably equivariant bundle, then you talk about the projectivization of the vector bundle. Then you get a toric variety, but with a bigger group action. And there you can do it the construction which you are talking about. And from this you have to see that whether it leads to the action on the, because projectivization of a toric bundle, this is again will be a toric variety with a bigger toric, and this action and that action will have some compatibility. So from there you have to see that whether the construction is, I don't know. So